At the end of the topic, you will be able to define electric current and its unit, construct a simple electric circuit, describe electric potential and potential difference.
The invention of electricity makes human life in the world more comfortable in all aspects. Electricity is used to operate not only the home appliances but also the industrial machines, medical instruments, spacecrafts, and so on. It is very important to learn about electricity and its utility. In this chapter, we will discuss electricity and its applications. When certain electric components like a bulb, a key or a switch and a conducting wire are connected to a battery in such a way that a closed path is formed for the current to flow, an electric circuit is obtained. We can define the electric circuit as follows. A continuous conducting path consisting of some electric components between the two terminals of a battery is called an electric circuit. A simple electric circuit consists of the following: source of electrical energy, device using the electrical energy, connecting wires made of conductors. The simple circuit shown here includes a cell, lamp, switch, and connecting wires. The cell supplies the energy required to force electrons around the loop, heating the filament of the bulb and causing the bulb to radiate heat and light. Flow of electrons through a material constitutes electric current. A simple circuit consisting of a source of electrical energy, a device that utilizes the energy, and conducting wires connecting them is shown. Click on the animation button to know more about the flow of electric current in a conductor.
The SI unit of electric charge is Coulomb. This is equivalent to the change contained in nearly 6 into 10 to the power of 18 electrons. The electric current is expressed by a unit called ampere, named after the French scientist. An instrument called ammeter is used to measure current in a circuit. Now, let's define an ampere. We know that I is equal to Q by T.
We can define electric potential as the amount of work done in bringing a unit positive charge from infinity to a specified point in space. It can be represented in the form of equation as electric potential is equal to the work done by charge, or V is equal to W by Q. The unit of electric potential is volt. The electric potential is 1 volt if 1 joule of work is done in moving a unit positive charge of 1 coulomb. It is represented as 1 volt is equal to 1 joule by 1 coulomb. We can define electric potential as the amount of work done in bringing a unit positive charge from infinity to a specified point in space. It can be represented in the form of equation as electric potential is equal to the work done by charge, or V is equal to W by Q. The unit of electric potential is volt. The electric potential is 1 volt if 1 joule of work is done in moving a unit positive charge of 1 coulomb. It is represented as 1 volt is equal to 1 joule by 1 coulomb. Potential difference. When moving a positive test charge within a uniform electric field from location A to location B, the difference in electric potential between locations A and B is referred to as the electric potential difference. It is represented as V is equal to VBA, which is equal to VB minus VA. Same as how an electric motor pumps the water to a tank at a higher altitude, a battery supplies potential to the charges, pushing it to a higher potential. Like the pipes, the conductors allow the flow of charges. Click on the animation button to have a comparative study on the flow of water due to pressure difference and flow of charge due to potential difference. Some of the common electrical components are as follows. A cell or a battery to maintain a constant potential difference due to the chemical reactions which take place inside it. Switch to open or close the circuit. Lamp that consume power to emit heat and light. Ammeter to measure current. Voltmeter to measure voltage. Fixed resistor that has constant resistance to control the flow of current. Variable resistor that has different values of resistance to control the flow of current.
In this topic, you have learnt electric current is the rate of flow of charge. Electric potential is the difference between 2 points in an electric circuit carrying current as the work done to move a unit charge from one point to the other. 1 volt is the potential difference between 2 points in a current-carrying conductor when 1 joule of work is done to move a charge of 1 coulomb from one point to the other. When 1 coulomb of charge flows in 1 second across any cross-section of a conductor, the current in it is 1 ampere. At the end of the topic, you will be able to state Ohm's law, determine the relationship between the potential difference across a conductor and the current through it, define resistance of a conductor.
George Simon Ohm was a German physicist born in Erlangen, Bavaria on March 16, 1787. As a high school teacher, Ohm started his research with the recently invented electrochemical cell invented by Italian Count Alessandro Volta. George Simon Ohm was able to define the fundamental relationship between voltage, current, and resistance. These fundamental relationships are of great importance that they represent the true beginning of electrical circuit analysis. Ohm's law gives the relation between potential difference and current for a conductor at a constant temperature. It states that the electric current I in a conductor is directly proportional to the potential difference V between its ends at a constant temperature T. Mathematically, V is proportional to I, V is equal to IR. The proportionality constant R is the electrical resistance of the conductor. The following animation explains the experimental verification of Ohm's law and determination of unknown resistance.
In an electrical circuit, the current flowing through a resistor between 2 points is directly proportional to the potential difference across the 2 points. Now, let us discuss the relation between the potential difference and the current in the circuit. Construct a circuit as shown. Close the circuit. When the bulb glows, measure the initial ammeter and voltmeter readings and tabulate them. Now, adjust the rheostat gradually. The current in the circuit varies. Now observe the corresponding voltage values in the voltmeter and tabulate the readings. From the observed readings, plot a graph with the voltage along the x-axis and current along the y-axis. It gives you a straight line which indicates the linear relationship between voltage and current. The slope of the line is a constant and is called the resistance.
The equation of Ohm's law can be written in other forms, which could be represented in the form of a triangle called magic triangle. Using Ohm's law, V is equal to IR, I is equal to V by R is equal to V by I.
In this chapter, you have learnt Ohm's law states that the current through a conductor is directly proportional to the potential difference V between its ends. V is directly proportional to I, or V by I is equal to constant. Resistance is the property of a conductor to resist the flow of charges through it. Its SI unit is ohm.
At the end of the topic, you will be able to deduce the equivalent resistance of resistors connected in series. Derive the equivalent resistance of resistors connected in parallel. Now, let us learn series combination of resistors and their equivalent resistance. In series circuit, resistors are connected end to end. Visual shows resistors R1 and R2 are connected end to end and connected to battery terminals. In such a circuit, same current exists in all of the resistances. The voltage across a group of resistors connected in series is equal to the sum of all the voltages across the individual resistors. Click on the animation button to know more. Now, let us learn series combination of resistors and their equivalent resistance. In series circuit, resistors are connected end to end. Visual shows resistors R1 and R2 are connected end to end and connected to battery terminals. In such a circuit, same current exists in all of the resistances. The voltage across a group of resistors connected in series is equal to the sum of all the voltages across the individual resistors. Click on the animation button to know more. Let us consider two resistors of R1 and R2 connected in series. Let V1 and V2 be the potential differences across them. The current Is across the resistors is the same. Applying Ohm's law, we have V1 is equal to Is R1. V2 is equal to Is R2. Since voltage drop V across the group of resistors connected in series is equal to the sum of all the voltages across the individual resistors. V is equal to V1 plus V2. Substituting the values of V1 and V2, V is equal to Is R1 plus Is R2 is equal to Is into R1 plus R2. Replacing the series of resistors by a single resistance such that the same current Is exists in the circuit, we get V is equal to ISR. Substituting the value of V in the above equation, we get ISR is equal to Is into R1 plus R2. From this, R is equal to R1 plus R2. Thus, R is called the equivalent resistance of series combinations of R1 and R2. When resistances are connected in series, their equivalent resistance is equal to the sum of the individual resistances. From this, we understand that the effective resistance of a series combination of resistors is more than the maximum resistance of the resistors in series. Next, we will discuss the parallel combination of resistors. In a circuit, if resistors connected to a common terminal are said to be in parallel connection, there exists the same potential difference across all of them. The current across the group of resistors connected in parallel is equal to the sum of all the currents across the individual resistors. Click on the animation button to know more. Now, we will derive the equivalent resistance of the parallel combination of resistors. Let R1 and R2 be the resistors connected in parallel. I1 and I2 be the currents through resistances R1 and R2. Same voltage V exists across the resistors. Applying Ohm's law, we have I1 is equal to V divided by R1, I2 is equal to V divided by R2. Since current across a group of resistors connected in parallel is equal to the sum of all the currents across the individual resistors, Ip is equal to I1 plus I2. Substituting the values of I1 and I2, Ip is equal to V divided by R1 plus V divided by R2 is equal to V into 1 by R1 plus 1 by R2. Replacing the parallel combination by a single resistance such that the same potential difference exists across it, the current value becomes, substituting IP in the above equation, we get IP is equal to V by R. V by Rp is equal to V into 1 divided by R1 plus 1 divided by R2. Simplifying the equation, we get the final formula as Rp is equal to R1 R2 divided by R1 plus R2. When resistances are connected in parallel, the reciprocal of their equivalent resistance is equal to the sum of the reciprocals of the individual resistances. Therefore, the effective resistance is less than the minimum resistance of the resistors in the parallel combination. In this topic, you have learned resistor is a device which limits the flow of current in a circuit. In a series combination, the resistors are connected end to end. The equivalent resistance of series combination of resistors is the sum of resistances of all resistors. When resistors are connected in parallel, the reciprocal of effective resistance is equal to the sum of reciprocal of individual resistance of resistors.
At the end of the topic, you will be able to define the heating effect of electric current, determine the factors that govern the heating effect of electric current.
Take a wire and connect it with a power supply. When the power supply is switched on, electric current flows through the wire and the wire gets heated up. Therefore, electrical energy is converted into heat energy. Do you know how? Electricity is due to the flow of charged particles such as electrons. When electrons are flowing inside the conducting wire, they are obstructed by atoms present in it. This obstruction for the flow of current is called resistance, which causes the emission of heat. Thin and long wire has high resistance. Therefore, thin wire produces more heat.
Now, let us learn the relation between the electrical work done and quantity of heat produced. If current I passes through an appliance of resistance R for time t due to applied electric potential V, the work done by the electrical energy W is equal to VIT, or W is equal to I squared RT. If Q is the quantity of heat produced, then Q is equal to W by J, since W is equal to JQ. Q is equal to VIT by J is equal to I squared RT by J. Here, J is constant. Therefore, Q is directly proportional to I squared RT.
This is known as Joule's law of heating. The law implies that heat produced in a resistor is directly proportional to the square of current for a given resistance, directly proportional to the resistance for a given current, and directly proportional to the time for which the current flows through the resistor.
We have learnt the basic idea of heating effect of electric current. Now, we are going to learn its real-life applications. Heating effect of current plays a vital role in our real life, such as electric bulbs, electric stove, electric iron box, and soldering iron.
Electric fuse is a safety device that works on the principle of heating effect of current. Fuse wire is made of an alloy of tin and lead. When large current passes through the circuit, the fuse wire gets heated up and melts away. Hence, the circuit is broken and further damage is prevented.
In this topic, you have learnt Joule's law of heating implies that heat produced in a resistor is directly proportional to the square of current, the resistance, and the time for which the current flows through the resistor. A fuse is one of the common devices that use Joule's heating effect of electric current. It is mainly used to protect circuits and appliances during the flow of any unduly high electric current.